Assalamualaikum warahmatullahi wabarakatuh. We are from Group 1. Today we will present about the algebraic and order properties of R. But before that, let me introduce the member of our group. The first is me, Zahra Cahyani with ID number 007, and then Kurnia Setyanti with ID number 076. The next is Aidah Salma with ID number 081. And then the next is Leilita Shiva Elfitria with ID number 116. And the last is Ayu Irfa Soraya with ID number 133. Okay, the first material is the algebraic properties of R. There are two properties. The first is addition. In addition itself, we have four properties. For the first is commutative property of addition. These are the properties. A plus B equals to B plus A. For the second property is associative property. Is the parenthesis of A plus B plus C equals to A plus parenthesis B plus C. For the third property is existence of zero element. If there exists an element 0 in R such that 0 plus A equals to A and A plus 0 equals to A for all A in R. And for the last properties of addition is existence of negative elements. For each A in R, there exists an element negative A in R such that A plus parenthesis of negative A equals to 0 and parenthesis of negative A plus A equals to 0. For the next properties is multiplication properties. In multiplication itself, we have 5 properties. The first is commutative property. A times B equals to B times A. For the second property, we have associative property, parenthesis A times B times C equals to A times parenthesis B plus C times C, For the third property, we have existence of a unit element. If there exists an element 1 in R distinct from 0 such that 1 times A equals to A and A times 1 equals to A. For the next property, we have existence of reciprocal. For each A is not equal to 0 in R, there exists an element 1 over A in R such that A times parenthesis 1 over A equals to 1 and parenthesis 1 over A times A equals to 1. And for the last properties of multiplication, we have distributive property of multiplication over addition. A times parenthesis B plus C equals to parenthesis A times B plus parenthesis A times C and parenthesis B plus C times A equals to parenthesis B times A plus parenthesis C times A for all ABC in R. And then we move to some theorems. Here we have the first theorem. In this first theorem itself, we have 3 theorems. The first is if Z and A are elements in R with Z plus A equals A, then Z is equal to 0. And for the second, if U and B is not equal to 0, are elements in R with U times B is equals to B, then U is equals to 1. And for the last theorem is if A is element of R, then A times 0 is equals to 0. And then we move to the next theorem. The second theorem, we have 2 theorems. In here, the first is if A is not equal to 0 and B in R such that we have A times B equals to 1, then B is equals to 1 over A. For the second one, if A times B equals to 0, then either A equals to 0 or B equals to 0.
The next is about rational and irrational number. So element of real number that can be written in the form A over B, where A comma B is element of integers and A isn't equal to 0 are called the rational numbers. So if we have numbers with form 1 over 2 or maybe 4 over 5 and so on in the form of fraction, then it can be stated as rational number. And how about the natural number? Is it rational number? So suppose we have a natural number 2 and we can state in the form 4 over 2 or maybe 10 over 5 or 2 over 1. So since this natural number can be stated in the fraction form, so the natural number can be subset of rational number. The set of all rational number in R will be denoted by the standard notation of Q. There also exists elements in R that are not in Q, not immediately apparent. For example, the diagonal of a square with unit side could then be expressed as a ratio of integer. In the view of the Pythagorean theorem for right triangle, this implies that the square of no rational number can equals to 2. So the model, we can write it as R squared is equal to 2. Then these elements of R that are not in Q become known as the irrational numbers. There doesn't exist a ratio number R such that R squared is equals to 2. And for the solution, we suppose on the contrary that P and Q are integer such that P over Q squared equals to 2. We recall that a natural number is even if it has the form 2n for some n element of natural number, and it is odd if it has the form 2n minus 1 for some n elements of natural number. Every natural number is either even or odd, and there is no natural number but even and odd. So we assume P and Q are positive and have no common integer factor other than 1. Since P squared is equal to 2 squared, from this equation we can write as P squared over Q squared is equal to 2, right? So we can write this form into this P squared equals to 2Q squared. We see that P squared is an even number, right? This implies that P is also even, because if P is 2n over 2n minus 1 is odd, then its squared, P squared is 2 times 2n squared minus 2n plus 1 minus 1 is also odd. And therefore, since P and Q don't have 2 as a common factor, they have common factor 1, then the Q must be an odd natural number. And then since P is even, then P can be written as 2m, for some m is element of n. And hence we can write P squared as 2m squared, and it's equal to 4m squared, and it will be equal to 2q squared. As the first equation, we have P squared is equals to 2q squared, right? So that we can write it into 2m squared is equals to q squared. Therefore, we get in here q squared is an even number. And it can follow that q is also even natural number. Since the hypothesis that p over q squared is 2 leads to the contradictory conclusion that q is an odd natural number and q is also even natural number, so it must be false.
Okay, the next is the order properties of R. There is a non-empty subset P of R called the set of positive real numbers that satisfies the following properties. Number 1, if AB belongs to P, then A plus B belongs to P. Number 2, if AB belongs to P, then AB belongs to P. And the last is if A belongs to R, then exactly one of the following holds: A element of P, A equals to 0, and negative A element of P. The definition of the order properties of R, type A be element of R, and the first is if A minus B element of P, then we write A more than B or B less than A. And the second is if A minus B element of P, and P compound of the empty set, then we write A more than equal to B and or B less than equals to A. The trichotomy property 3 implies that for A be element of R, exactly one of the following will hold A more than B equals to B and A less than B. Therefore, if both A less than equals to B and B less than equals to A, then A equals to 0. For notational convenience, we will write A less than B and B less than C to mean that both A less than B and B less than C are satisfied. The other double inequalities A less than equals to B and B less than C, A less than equals to B and B less than equals to C, and A less than B and B less than equals to C are defined in a similar manner. To illustrate how the basic order properties are used to derive the rules of inequalities, we will now establish several results that the reader has used in earlier mathematics course.
Okay, the next we have theorem of order properties of R. We have four theorem. First, we have let A, B, C be any elements of R. So that means if A more than B and B more than C, we have A more than C. So the second one, we have if A more than B, then A plus C more than B plus C. And then the third, we have if A more than B and C is more than 0, then C times A more than C times B. But if A more than B and C is less than 0, that means we have C times A is less than CB. So what is the proof of the theorem? First, the first proof, if A minus B is in P and B minus C is in P, then if A belong to P, then A plus B belong to P. It implies that A minus B plus B minus C equals A minus C. So it belongs to the P. Hence, A is more than C. And then for the second one, we have if A minus B is in P, then A plus C minus B plus C equals to A minus B is in P, thus A plus C is more than B plus C. And then the next one is the last is if A minus B is in P and C is in P, then CA minus CB is equal to C times A minus B is in P. By if A, B belong to P, then AB belongs to P, thus C times A is more than C times B when C is times 0. Meanwhile, if C less than 0, then minus C, B minus C is in P, so that CB minus CA is equal to minus C times A minus B is in P. Thus, C times B more than C times A when C is less than 0. For the second theorem, we have three. First is we have if A is in R and A is not equals to 0, then A squared is more than 0. And for the B is 1 more than 0, and the C is if small n is in N, then small n is more than 0. So what is the proof? First, we have the first theorem in A. So by the trichotomy property, if A is not equals to 0, then either A is in P or minus A is in P. So if A is in P, then by if AB belong to P, then AB belongs to P, we have A squared equals A times A is in P. Also, if A squared equals to minus A times minus A is in P, we conclude that if A is not equals to 0, then A squared is more than 0. And for the B proof, we have since 1 is equal to 1 squared, right? So it follows from the proof of A that 1 is more than 0. And for the C is we have to use mathematical induction to prove it. The assertion for n is equal to is true by the B, by proof B, that if we suppose the assertion is true for the natural number k, then k is in P. And since 1 is in P also, we have k plus 1 is in P by if A, B belongs to P, then A plus B belongs to P. Therefore, the assertion is true for all the natural numbers. Okay, next we have the third theorem. It is if A is in R is such that 0 is less than or equals to A, and then less than epsilon for every epsilon more than 0, then A is equal to 0. So the proof the proof is supposed to the contrary, that a is more than 0, then if we take epsilon 0 equals to 1 over 2a, we have 0 less than epsilon 0 less than a. So therefore, it is false that a is less than epsilon for every epsilon more than 0. So we conclude that a is equal to 0. Okay, and then for the last theorem, which is the fourth theorem, we have if a times b more than 0, then either one, a is less than 0 and b is more than 0, or the second condition is a is less than 0 and b is less than 0. So the proof is, first note that a times b is more than 0, so that means a is not equal to 0 and b is not equals to 0. From the trichotomy property, either a is more than 0 or a is less than 0. If a is more than 0, then 1 over 2 more than 0, right? So, and therefore, b is equals to 1 over a times b more than 0. Similarly, if a is less than 0, then 1 over a is also less than 0. So that b is equals to 1 over a times ab less than 0. Okay, this is for the corollary. If a times b is less than 0, and then either 1, a is less than 0 and b is more than 0, or 2, a more than 0 and b is less than 0.
The next is about inequalities. We now show the order properties presented in this section can be used to solve certain inequalities. For example, number 1, determine the set A of all real numbers x such that 2x plus 3 is less than or equal to 6. Note that we have x element of A if and only if 2x plus 3 less than or equal to 6, if and only if 2x less than or equal to 3, if and only if x less than or equal to 3 over 2. Therefore, A is equal to x, element of real number where x less than or equal to 3 over 2. Number 2, determine the set P is the set of x, element of real number where x squared plus x greater than 2. Rewrite the inequality so that theorem 4 of the order properties of R can be applied. Note that x element of B if and only if x squared plus x minus 2 greater than 0, if and only if x minus 1 times x plus 2 greater than 0. Therefore, we either have x minus 1 greater than 0 and x plus 2 greater than 0, or we have x minus 1 less than 0 and x plus 2 less than 0. In case 1, we must have both x greater than 1 and x greater than minus 2, which is satisfied if and only if x greater than 1. In case 2, we must have both x less than 1 and x less than minus 2, which is satisfied if and only if x less than minus 2. We conclude that P is equal to x element of real number where x greater than 1, union of x element of real number where x less than minus 2. Number 3, determine the set C is the set of x element of real number where 2x plus 1 over x plus 2 less than 1. We note that x element of C if and only if 2x plus 1 over x plus 2 minus 1 less than 0, if and only if x minus 1 over x plus 2 less than 0. Therefore, we have either x minus 1 less than 0 and x plus 2 greater than 0, or x minus 1 greater than 0 and x plus 2 less than 0. In case 1, we must have both x less than 1 and x greater than minus 2, which is satisfied if and only if x less than 1 and x greater than minus 2. In case 2, we must have both x greater than 1 and x less than minus 2, which is never satisfied. We conclude that C is the set of x element of real number where x less than 1 and x greater than negative 2. The following example illustrates the use of the order properties of real number in establishing certain inequalities. It should be noted that the existence of square roots of positive number has not yet been established. However, we assume the existence of these roots for the purpose of these examples. Examples number 1. If a and b are positive real numbers, then their arithmetic mean is 1/2 times a plus b, and their geometric mean is square root of ab. The arithmetic geometric mean inequality for ab is the square root of ab less than or equal to 1/2 times a plus b, with equality occurring if and only if a is equal to b. To prove this, note that if a greater than 0, b greater than 0, and a is not equal to b, then the square root of a greater than 0, the square root of b greater than 0, and the square root of a is not equal to the square root of b. Therefore, it follows from theorem to a of the order properties of R that the square root of a minus the square root of b square greater than 0. Expanding this square, we obtain a minus 2 times the square root of ab plus b greater than 0. Whence it follows that the square root of ab less than 1/2 times a plus b. The further explanation can be seen in this section. The next is about example number 2, Bernoulli's inequality. If x greater than -1, then 1 plus x to the power of n greater than or equal to 1 plus nx for all n element of natural number. The proof uses material induction. The case n equals to 1 yields equality. So the assertion is valid in this case. Next, we assume the validity of the inequality 1 plus x to the power of n greater than or equal to 1 plus nx for k element of natural number, and will deduce it for k plus 1. Indeed, the assumption that 1 plus x to the power of k greater than or equal to 1 plus kx, and that 1 plus x greater than 0 imply that 1 plus x to the power of k plus 1 is equal to 1 plus x to the power of k times 1 plus x. Thus, inequality 1 plus x to the power of n greater than or equal to 1 plus nx holds for n equals to k plus 1. Therefore, 1 plus x to the power of n greater than or equal to 1 plus nx holds for all n element of natural number. That's from group 1. Sorry if there are mistakes. Wassalamualaikum warahmatullahi wabarakatuh.